Welcome to Part A of Lecture 4 for Differential Equations in Linear Algebra. You can see in Lecture 4A we're going to continue looking at a pendulum, in this case a double pendulum with two rods and two bobs, two masses that are swinging back and forth and are attached to each other. We'll look at something called the Logistic Growth Model, again both in the discrete and continuous case. We'll look more at slope fields and I will introduce Euler's method. In Lecture 4B we'll do the linear algebra stuff, mostly focus on vectors, vector algebra, dot products, and we'll end with an example of a 2x2 system of linear equations. But let's once again start looking at the pendulum. The pendulum is an example of a nonlinear differential equation, and what we've seen in lectures 2 and 3 is that you can get some kind of complicated behavior, especially if you have some external forcing. Now in this case we're actually not going to have external forcing, it's going to be unforced. Also no friction, it's undamped, but it's still nonlinear, but also it's a double pendulum. You again have two rods with two bobs attached to them, and these penduli, I guess that would be the plural of pendulum, are attached to each other and swinging freely based on that. It's pretty wild motion, and once again it's going to be too fast to really tell what's going on here in the PowerPoint, so we'll look at the Mathematica where we can slow it down and see what's happening. There it is, there's the motion. You got the black one and the red one swinging together under the influence of gravity, assuming there's no external forcing and no damping. And we can let time go both forward and backward here. The differential equations that describe this motion are insanely complicated. You want to see them? Here they are in all their glory, or should I say gory. Alpha and beta are the two angles. I'm not specifying which angle is which for the red and the black penduli. Alpha double prime and beta double prime then are angular accelerations. Those would be in, say, radians per second squared. And you can see those second derivatives are complicated combinations of the angles and their derivatives themselves, involving sines, cosines, differences of angles, derivatives that are squared. Insanely kind of complicated system of differential equations. But you can derive this as a valid model for the behavior of such a double pendulum. We again have initial conditions. Alpha of 0 and beta of 0 are both 3, right there, close to pi, radians. And we have 0 initial angular velocity for both of them. We're letting them go from rest. Is it possible to solve this? No. We looked at simpler examples in lectures 2 and 3, and it wasn't possible to solve them then. Definitely with a more complicated system like this, it's not possible to solve. What about the phase space? Remember I emphasized this idea of a phase space, and really this is the most important thing to get out of this. I said the phase space, for example, for the unforced, undamped single pendulum involved a plane with two axes that were labeled with the angle and the angular velocity. And at each moment in time, there's a point that moves around that plane describing the motion. If we pause that at any instant in time, it gives you the angle and it gives you the angular velocity of that pendulum. In this case, we've got two angles and two angular velocities. The phase space would be four-dimensional. Wow. Higher dimensional space, an application of higher dimensions. Can we visualize it? Well, we can try. There are some techniques to try to visualize such a higher dimensional phase space, and we will try to do that to some degree, but it is certainly difficult. But it is very interesting. Let's look at the Mathematica as well, just to slow this down and show you that it does seem reasonable that this is modeling something in a reasonable way. Here's the code that solves the system of differential equations, essentially. By the way, in lecture 5 and 6, where you're going to get into Mathematica in more detail, if I enter this code, it gives me numerical approximations for alpha and beta as functions of time, and then I can use some other code to animate what we just saw there, and we can play it. And it is slower. You can look at that motion and get an intuitive physical feel for that and say, hey, that makes some sense that that could happen if there was no friction and these penduli were attached to each other like this. It makes some good physical sense, and it's pretty interesting, pretty wild, pretty chaotic. In the end, it's pretty unpredictable, and that's one big lesson as well in all of this. We are, for the most part, going to be looking at simpler systems, but I want to alert you to all these more complicated systems to show you that differential equations can be applied in more complicated situations. Okay? All right, let's go on to the logistic model. As we've done in lectures 1, 2, and 3, we're going to talk both about discrete and continuous models. Pretty soon we're going to focus mostly on the continuous until we can bring in some matrix algebra to talk about discrete dynamical systems in the context of the linear algebra content. In the logistic model, we assume the relative rate of growth is a linear function of the population, in other words, the population's size. And in the discrete case, I'm going to make an extra simplification. I'm going to let yn not be the number of fish or bunnies or whatever at time n, but the number of fish or bunnies divided by the carrying capacity of the environment. Okay, this is most easy to imagine for fish in a lake, say. All right, the lake is finite in size. There's finite food resources for the fish. There's a certain carrying capacity that the lake can sustain of this species of fish. You know, it could be 1 million fish if it's a fairly large lake. And we're looking at the ratio of this. So when this ratio equals 1, that means that the population is at the carrying capacity. If it's less than 1, then the population is below the carrying capacity. And if it's greater than 1, the population is above the carrying capacity. We're going to assume that this quantity that you see right here, this ratio, which can be thought of as a relative rate of change, it's a discrete relative rate of growth in this case because you're taking the total change in the population from time n minus 1 to time n and dividing by the population at time n minus 1. You would think of this as a percent. You know, typically it might be, say, 10% per unit time. It's proportional to this quantity, 1 minus the population at time n minus 1, where k is the constant of proportionality. Think about this intuitively. If the population is fairly low compared to the carrying capacity, yn is going to be pretty close to 0, yn minus 1, say. 1 minus yn minus 1 is going to be pretty close to 1, and it's certainly going to be positive. K will be pretty close to the relative growth rate when yn minus 1 is close to 0. On the other hand, if yn minus 1 gets close to 1 but still less than 1, this is still positive but close to 0, the relative rate of change is going to be small but still positive. When yn minus 1 is above 1, so that the population is large above the carrying capacity, probably more fish are going to die than are going to be born. The population is probably going to decline. And in fact, that does fit the model here. 1 minus something bigger than 1 would be negative. K times a negative number would still be negative because I'm assuming K is positive. The relative rate of growth would be negative in that case. All right, so what do we want to do? We want to solve this difference equation. Let's do what we did before. Solve it for yn in terms of yn minus 1. And by the way, like I mentioned in lecture 3, it makes some sense to call this a difference equation because you do see a difference up there. However, when you write it this way, you don't see a difference, except right there, but that's not a big deal. So what did I do to get from here to here? I multiplied both sides by yn minus 1. That gives you the yn minus 1 that you see here. And then I added yn minus 1 to both sides to get rid of it on the left side. That's the yn minus 1 that you see right there. This is the function, this is the difference equation or recursive equation that I'd like to solve for yn if possible. Let me also emphasize that you could write it this way. It might be better to think of it this way, in fact. You can group the yn minus 1 to the first powers from this term and this term times 1 right there to get a 1 plus k in parentheses times yn minus 1. And the yn minus 1 squared term would come from distributing this over here. And you'd have a minus sign still there. That's another way to think of this function that I'm plugging yn minus 1 into. If I wanted to write f of y as just a function of y, based on what we see here, I'd write it as 1 plus k times y minus ky squared. I'm replacing y with yn minus 1 and replacing the left-hand side with yn to get this thing called the difference equation. What do we do in lecture 3 to solve a difference equation? We essentially iterated. We applied it over and over again. Is that possible here? Well, yes. But it's so difficult that I'm also saying not really. You can't really get a simple pattern here. Let's see what happens. So here's the difference equation again, solved for yn as a function of yn minus 1. What we need to do to try to solve this for yn directly is we would need to replace the yn minus 1s here, and here, with what they would equal in terms of yn minus 2, right? These recursive equations are true no matter what the subscript is. Y sum subscript is f of y sum preceding subscript. If this is an n, this would be an n minus 1. If this is an n minus 1, this would be an n minus 2. If this is an n minus 2, this would be an n minus 3. That's the idea of a difference equation like this. So go ahead and replace those yn minus 1s with this expression except replace those yn minus 1s with yn minus 2s, like this. Right here and here. I've replaced yn minus 1 here and here with what it would equal based on the difference equation in terms of yn minus 2. Excuse me. Yikes! Already, in just one iteration, it's pretty complicated. I guess you'd call it 2 iterations, actually. I mean, yes, I could continue simplifying. I could distribute the 1 plus k through here. I could distribute the k through here, there, after squaring it, in fact. And then I guess I'd have to replace the yn minus 2s with this expression involving yn minus 3s. I don't think I want to do that. Yikes! And you'd want to do it again and again and again. In fact, you'd want to do it, what would it be? N times, essentially, to get it in terms of y0, to get yn in terms of y0. I don't want to do that. You don't want to do that. Pretty much nobody wants to do it. It's not really possible to solve this in a simple way. So do we give up? Well, no, we can turn to the computer. Why, that won't erase. That happened to me before. We could just try picking something for k and y0 and use technology to see what happens. Suppose k is 3 and y is 0.1, for example. Then plug in k equals 3 and y equals 0.1. K equals 3 right there, and right there gives you the 4 right here because it's a 1 plus k, and the 3 right there because of the k there. And y0 is 0.1. You get a 0.1 right there, and 0.1 squared is right here. Go ahead and take your calculator out and check this. You do get 0.37. By the way, we got a lot of content to cover in this first lecture, so I'm not going to give you a you-try example for you to work on, but you certainly can pause the video anytime you want to double check things. Then apply this again to find y2. Okay, so once again we have 1 plus k and k giving you a 4 and a 3. I'm taking k to be 3. y3, it just was something I picked. Didn't have to pick 3. y1 is the 0.37 right there and there. I have to plug in 0.37 right there and 0.37 squared right there, and you should double check that you get 1.0693. So what's happened here so far in terms of the fish in the lake? At time 0, they were 10% of the carrying capacity. If the carrying capacity is 1 million, then the number of fish would be 100,000. At time 1 month, 1 year, whatever later, they were at 0.37 for yn. y1 was 0.37. 37% of the carrying capacity would be up to 370,000. At time 2, we're up above 1. In other words, the actual population is above 1 million. That probably means the population goes down the next period, and it does. y3 is about 0.84699. And then we can do it again to find y4, and we get about 1.23578. What would we predict for the long-term behavior of this sequence of numbers here? It's not so clear. And in fact, if you use technology to keep going, you get the following graph of the population as a function of n, where n is 0, 1, 2, 3, etc., discrete. However, I'm going to connect the dots because it makes it easier to see that there's really no clear pattern other than the fact that when the population is above 1, the next time period it goes below 1. If it's below 1, it doesn't necessarily go above 1 the next time period. For example, right at the start it doesn't. When it's in these spots down here, the next time period it doesn't go above 1. So it's pretty seemingly random and confusing behavior. What in the world is going on here? This is an example of chaotic behavior. And something else that's very interesting about it is if I change this initial condition ever so slightly, in fact, an arbitrarily small change from 0.1 to say 0.11 or even 0.101 or 0.1001, it would look pretty similar at first, but in the long run it would be very different. And we would see that. Maybe I'll even do that for the next lecture to show the overlap between those. Well, there's basically no overlap in the long run. That's called sensitive dependence on initial condition. That's another hallmark of chaos. What about a continuous model? That's a differential equation. And again, this course is differential equations and linear algebra. We do focus more on differential equations than difference equations. Though I think it's good to bring difference equations in to compare and contrast for one thing, and also in linear algebra, we will be doing difference equations involving matrices later on. Now I am going to do the number of fish at time t instead of the fraction of the carrying capacity. This is a little bit more traditional in this context. Y is the number of fish. I'm calling it phi of t. Just like in lecture 3, phi of t is my solution function. It's a function of t. Phi is the name of the function. If you prefer calling it phi, you can. You can say phi of t. I'm going to usually say phi of t. What are we going to assume? The same thing. The relative rate of growth is a linear function of the population. It's going to be a little different, though, than the discrete case. First of all, this quantity right here, dy dt divided by y, is, in this continuous case, the instantaneous, emphasis on the word instantaneous, relative rate of growth, or I should say rate of change. It's not always growth. Dy dt is the rate of change, the instantaneous rate of change, the derivative, right? If you divide that by y, the current population, say, that would give you an instantaneous relative rate of change. You know, typical values here might be, again, 0.1 or 0.2 for 10% or 20% continuous growth. I'm going to assume it's this linear function of y, some constant k, times 1 minus y over L for some constant L, that's also positive. L actually is the carrying capacity here. L kind of reminds you of a limit. It's sort of a limiting population. Does wild behavior happen in the continuous case like it happened in the discrete case? The answer is no. It's more well behaved, which then makes you think this could be better. But maybe, you know, real life is kind of chaotic, so maybe the discrete model is better. You don't know for sure until you compare it against reality. So let's write this in the standard form. Let's multiply both sides by y and get just a dy dt on the left side. Here we go. Here's the standard form of the differential equation. So it's dy dt equals this. I went from here to here by multiplying by y. I can also describe this thing as a function of y. Call it f of y. No need for subscripts here with differential equations. Okay. Y is a continuous function of t. You need to keep reminding yourself of that. That's really important. And that's part of the reason why I'm adding the extra notation there to emphasize it's a function of t, whereas our main textbook doesn't do that. All right. By the way, this is called an autonomous equation. I haven't mentioned that word yet. This is my first time. Autonomous differential equation, ODE for ordinary differential equation. The right-hand side only depends on y. It's independent of time. You know, the word autonomous basically means independent, like an autonomous country, region. Independent. In this case, autonomous means independent of time. The model, so to speak, isn't changing over time. Is that right? Is it realistic to model it this way? I'm not saying it's realistic or not. You, again, would have to compare it with actual data. Maybe a non-autonomous model would be better. For example, with fish, if you want to take into account fishing, which varies over the course of the year, over time, maybe you want a non-autonomous model where you're subtracting, say, some sinusoidal term. Let you think about that. We want to solve this. Somewhat amazingly, this is possible to solve. Is this possible to solve? Somewhat amazingly, yes. And we can use separation of variables, which we've talked about already. Along with some extra stuff, the method of partial fractions and some slick algebra. This is not an easy one to solve. It's pretty tricky. You can get tripped up at a number of points. But it's something my students, and pretty much anybody else in this course, learning from me, should attempt. Maybe you want to pause it here and try to attempt it. Let's go ahead and do it the standard way where we imagine dy dt as a fraction, even though it's not. And multiply both sides by dt first to get the t on the right side. But we have y's on the right side. We want to divide both sides by this expression, y times 1 minus y over L, to get that in the bottom on the left side and cancel it from the right side. That's the separation of variables part. And we get this equation. I'll remind you what technically is going on here when we are finished solving it here. When you see something like this, you should start shaking. Oh, must integrate. And that's, again, in this class, usually a good thing to do. Integrate both sides. The right-hand side, as usual, is easy. The left-hand side is harder in this case. You do need the method of partial fractions to rewrite this fraction here, this integrand, like this. Now, I'm not going to show you the details. If you took Calculus 2, a second semester of calculus, or AP Calculus BC, you should have done it. That's another place you might want to pause and try that to see that this function and this function are the same thing. Different ways of writing the same function. You can always double check it, by the way, by adding these two fractions, by getting a common denominator to go from here to here. And the reason you do that is because those things are easy to integrate. You're going to get logarithms. The natural log of the absolute value of y there, and the natural log of the absolute value of L minus y, with also an extra factor of -1, because the minus sign there, that's a place where people get tripped up. If you do a substitution here to help you integrate that function right there, you'd want to let u, say, equal L minus y, and then du would be negative dy. You can always check it by differentiation. I did a couple steps there. I also used the property of logarithms to rewrite it this way. This thing right here is the same as ln of the absolute value of y minus ln of the absolute value of L minus y. That's a property of logarithms. The log of a quotient is the difference of the logs, and the absolute value signs don't matter. I could put absolute value signs around the top and the bottom individually, but that's the same as the absolute value of the whole thing. Always remember the goal. The goal is to solve for y. So we want to get rid of the logarithm. We need to exponentiate. And I use a C1, then a C2, and a C3. Ultimately, I want to just write a C. It still feels kind of complicated looking at this. Solve for y. I would multiply both sides by L minus y first to cancel on the left. You get a bit L minus y on the right. You'd have to distribute that through and bring all the y terms back to the left. Here are the details. Well, okay, I skipped some details. Bring all those y terms back to the left and then divide by what y is being multiplied by, which is this. You should take the time to check that. I am skipping some steps here. And this can be simplified a little bit. You could, for example, divide the top and the bottom by C3. So there's no C3 up there. C3 divided by C3 is 1. You get the 1 right there. What else did I do? I also divide the top and bottom by e to the kt. Canceling the e to the kt up there. E to the kt divided by e to the kt is 1. Once again, emphasizing that this part is what gives you the 1. I kind of switch these around in the bottom here. And then this part right here is really 1 over C3 times e to the kt. So I can write it as, say, c, where c is 1 over C3, times e to the negative kt. I've skipped some steps. You should check this. Now let's use an arbitrary initial condition. Y sub 0 equals y of 0. Plug in t equals 0. E to the 0 is 1. So I get L over 1 plus c. My goal is to solve for c in terms of y0. L is some fixed number that I'm not specifying. C is an arbitrary number in general, but I want to get it in terms of y0. So I'd want to multiply both sides by 1 plus c and divide both sides by y0. And then I would want to subtract 1. And then if you simplify it a little bit more, you should check that you get this. Now what I'd want to do is I'd want to take that expression for c and substitute it back in here. Right there in place of that c. To get my unique solution of the initial value problem where y0 is the fixed initial condition. And then you'll have fractions within fractions. If you want to get rid of those fractions within fractions, you can multiply the top and the bottom by y0. Here's the final answer. And I'm also adding the phi of t in. That's the unique solution of the initial value problem where y of 0 is the specific number y sub 0. Okay? And you can check this also by plugging in the left-hand side and the right-hand side and simplifying and seeing that you get the same thing. All things that are worthwhile to do. Before we go into the next slide where we make use of this function and graph it and think about it in the slope field, I do want to remind you that, technically speaking, you can justify a little more rigorously at least, this separation of variables idea by thinking of the differential equation in the form phi prime of t for dy dt equals, replace the y's with phi of t, k times phi of t times 1 minus phi of t divided by L. And then you do the same kind of algebra operation that we used to get from here to here, but when you do that, you're not really thinking of this as a fraction anymore. It's the derivative. I would divide both sides by phi of t and also 1 minus phi of t over L. And I get a phi prime of t over those things on the left side, which is essentially what we have here. The y is the same as phi of t, and the dy is really phi prime of t dt. You can do a substitution to get from an integral involving the phis to this integral involving y. Okay? Talked about that more carefully in lecture 3. Once again, this is something you should check, and it's worthwhile. It's worth your while if you want to understand the material to do that. Let's look at a logistic model solution. Let's pick L to be 1. I picked thousands of fish. I could have picked millions of fish, depending on the size of the lake. K to be 0.04, which essentially means when the population is small, it's growing at an instantaneous relative rate of change of 4% per unit time. That's essentially what that means. And I'm going to add a little bit of extra notation here to emphasize the dependence of the solution on the initial condition. And I'm also going to take t to be months. That'll be helpful for the next slide. And write this. This extra y sub 0 that I put in here as a subscript of the phi right there, that's what I'm doing to emphasize the dependence on the initial condition. Think of y sub 0 as a fixed number, and this thing here is a function of t. Notice L is 1, and k is 0.04. You have an e to the negative kt there, for example. This is going to be a helpful notation for us, for Mathematica programming, for one thing, and for some more complicated ideas that we're going to encounter later in the course. So, my students, you definitely should pay attention to this. And so, for instance, if the initial population was 0.1000 fish, which would be, 100 fish, then our population model would be this function. Plug in y0 equals 0.1. I've got it in the subscript right there. I'd also need to plug in 0.1 here, here, and here to get a 0.1 there, a 0.1 there, and a 1 minus 0.1, 0.9 there, e to the negative kt. And I could graph this function. And I could graph it in the slope field. Now, I introduced the idea of the slope field last time. We're going to continue talking about slope fields here in this lecture and even in the next one. Looks like this. And in a quick nutshell, I'm going to show you a couple more examples of slope fields as well. You make a ty plane, and you make a bunch of line segments in some grid of points with certain slopes. And the slopes are determined by the function that's the f function of the right-hand side of the differential equation right there. The slope is f of 0.75 in this example right here because y is 0.75 right there. I'm plugging 0.75 into the function. F of y was ky times 1 minus y over L. And if L is 1 and k is 0.04, that's 0.04 y times 1 minus y. You should check, replace y with 0.75 here and here. You will get 0.0075, and that is the slope, the rate of change of these solution curves when they pass through this horizontal line at y equals 0.75. And it's the slope of all the red lines along that horizontal line. That's the idea of a slope field. You make at the grid of points, you plug the coordinates of the midpoints of these line segments into this function to figure out the slope. And then the key idea is the solutions have to follow the slope field. Anytime one of these solution curves that are colored here, cyan, blue, green, pink, orange here, anytime they pass through one of the midpoint of one of these line segments, they have to have a tangent line that's parallel to the line segment. Essentially, the line segment is a tangent line. And they have to have that rate of change, that slope at that point. For an autonomous equation, the slopes are constant along horizontal lines because y is constant along horizontal lines. And in the autonomous equation, f of y depends on y. Keep the distinction between these functions. F is just the right-hand side of the differential equation. Phi is a solution. F is not a solution. It just helps you figure out what solutions look like. It's the model, in a sense. Notice I've labeled these different solutions with different subscripts based on the initial conditions. Phi sub 0 t has an initial value of 0. If the population starts at 0, it stays at 0. That's an equilibrium solution. Phi sub 0.01 of t starts at 0.01. Phi sub 0.1 starts at 0.1 at time 0. Phi sub 1 starts at 1. That's another equilibrium solution. That's a constant function that solves the differential equation. Phi sub 1.3 starts at 1.3. Okay? Let's look at a couple more examples of slope fields. Well, okay. Let me just quickly show you this slide to show you that you should be able to use a logistic model to do some problem solving. Then we'll look at a couple examples. We can use this model to make predictions about future populations and solve for times when the populations will reach a certain level. Keep in mind that the model may not be perfect, so these are always estimates. And they may be good estimates and they may be bad estimates. For example, when y0 is 0.1 thousand fish, what's the predicted population at time equals 50 months? Think about that. All you have to do is plug in 50 in for t into that formula. There you go. Replace t with 50 right here. Go ahead and give this a try. Pause the video. You get an estimate of 0.451 thousand fish. On the other hand, how long does it take for you to get to 900 fish, which would be 0.9 thousand? Set the function equal to 0.9 and solve for t. Here are the details. It's an exponential equation. You can solve for t ultimately with logarithms after you've done some algebra. These are the steps. And this is telling you it's going to take about 110 months. Do notice again, like I mentioned 10 minutes ago or so, the behavior of solutions in that slope field and the formula we see here are different from the discrete case, the difference equation, where we couldn't really solve the difference equation and we got wild behavior. For the differential equation, it's better in a sense because it's tamer, for one thing, in its predictions, and we have formulas that we can actually work with. All right, yeah, let's look at a couple examples of slope fields, and then I also want to introduce Euler's method. Now I'm going kind of fast here, but these are all important things to do and think about. Whenever I do a topic, I always come back to it later though, so these are not the last times you're going to see these topics. More slope field examples. Here's a pure antiderivative problem. dy/t equals f of t, not f of y, equals 1/2 t squared minus 2t, or y of 0 equals some fixed number y sub 0. That's called a pure antiderivative problem. We can separate variables to solve this, but we don't really need to. This is saying find a function whose derivative is always equal to this. Just integrate this thing on the right. What would you get? You get 1/6 t cubed minus t squared plus c, where c is arbitrary. And c, in fact, would equal y0. The unique solution for a fixed y0 is this function right here. This is a pure antiderivative problem. Pure antiderivative problems are the simplest kinds of differential equations. You can solve them just by integrating, at least if the integral is easy to do or not too hard to do. What about the slope field? I'm going to make two slope fields, one that's plain with no solutions in it, and another one that's got some solutions. Here's the slope field for this differential equation. How would you make this if you had to? If you were forced to do this by hand, how would you make it? You'd pick a grid of points, probably not so many points as what you see here. So for example, we could consider the point 2, 1, right there. That point has coordinates ty coordinates, rectangular coordinates. This is what we've been talking about in the linear algebra portion of these lectures. 2, 1, t is 2, y is 1. To figure out how steep you should make this little red line there, what's the slope of that line segment, plug this point into the right-hand side function of the differential equation. But that only depends on t, so I only need the 2. The 2 is the only important thing. In fact, if you look along the vertical line at t equals 2, all these little red line segments that you see have the same slope. Just like for the autonomous equation, when we looked on horizontal lines, they all had the same slope. What would that slope be? Plug in 2 here. F of 2 is 1/2 times 2 squared is 1/2 times 4 is 2. And then minus 2 times 2 is minus 4. To get negative 2, the slope of this little red line segment right there is negative 2. If you continued it, rise over run would be negative 2. And that would be worth doing. Once again, solutions have to follow the slope field. And they have to be cubic functions. And it makes sense, you look at this, to think about that the solutions have to look like this. The subscript, again, specifies the initial condition. So phi sub negative 1 of t has an initial value at time 0 of negative 1. Phi sub 1 of t has an initial value of 1 at time 0. And phi sub 3 of t has an initial value of 3 at time 0. And these solutions are all vertical translations of each other. They're all antiderivatives of the same function. That should make good sense then. So for pure antiderivatives, slope fields are constant along vertical lines. For those autonomous equations, they're constant along horizontal lines. What if there's a mixture of t's and y's on the right side? Is that allowed? Sure, it's allowed. Right there. You got a t plus y on the right-hand side. Yeah, that is allowed. So if I try to make a slope field here, the slope of these line segments are going to depend on both the t and y coordinates of the points. They're not going to be constant along horizontal lines or vertical lines. It's going to be some sort of mixture. Is this equation possible to solve? Yes, though it does involve techniques that we haven't talked about. You can't solve it by separation of variables. If you try, you'll fail. How would you solve it? Probably the best method would be guessing, and I would encourage you to try guessing involving an exponential function. Here is the unique solution when y0 is fixed right here. Phi sub y0 t is a linear function plus a constant times the exponential growth here, where this constant depends on the initial value of y. Depends on y sub 0. Here's the plane slope field. Notice these slope marks don't have constant slopes along horizontal lines or vertical lines. Some sort of mixture. Here are some solutions. Notice the one that has an initial value of negative 1, when t is 0, is straight. It's not an equilibrium solution because it's not constant, but it is a linear function. It is straight. These other two that have other initial values at t equals 0 are not straight. They involve exponential growth, possibly with this blue on it, with a negative coefficient for the exponential growth. Okay, so this should make good intuitive sense. I would encourage you to double check this function solves the differential equation by differentiating it to simplify the left-hand side and plugging it in place of y right there and simplifying to simplify the right-hand side. You get two functions of t that are the same. It also satisfies the initial condition. If you replace t with 0 there, and e to the 0 is 1 right there, you're going to get a negative 1 plus y0. The negative 1 and plus 1 cancel, leaving you with y0. All right, this is our last topic. I know lots of quick topics here in this lecture. This is an introduction to Euler's method. We'll get into the details in the next 2 lectures. Here's the main idea, though. Euler's method provides a way of quantitatively approximating solution curves using what's called a numerical iteration scheme. Why would you need to do such a thing? Well, some differential equations, like that double pendulum, are so hard, so complicated, that we can't find formulas for the solutions. So we have to approximate the solutions. Numerically approximate means find approximate functional values, and then connect the dots in some way to see the graph. The basic idea is that for small jumps in time, solution curves should be well approximated by their tangent lines. The fundamental idea of differential calculus right there. And the tangent line slopes can be determined from the slope field. In other words, the right-hand side function, the f function, whether it's f of t or f of y or f of t comma y. Those right-hand side functions in any given situation determine the slope field and therefore the approximate solutions, the actual solutions and the approximate solution. Here is back to the logistic model. Phi sub 0.1 of t, more zoomed in though. And look over a small time interval, say from t equals 0 to t equals 5. This black line, which is the tangent line to the green curve at that point, pretty well approximates the green curve over that entire interval. It's a pretty good approximation. That's the basic idea. How do you find the slope of the tangent line? You plug into the right-hand side function. In this case, you plug in the second coordinate, 0.1. That's the y coordinate in this case. To get a slope of 0.0036, draw a straight line with that slope. It's the tangent line at that point. It well approximates the solution. The actual solution is concave up, so the approximation in this case is too low. It's an underestimate. So that's the basic idea, is use tangent lines. Here's the way the setup works. This is a little technical. I'm just going to go over it really quick. We'll again get into more details in lecture 5. Here's the general setup. Suppose we're given an initial value problem, dy dt equals f of ty. We are considering the most general situation here where we have a right-hand side function f that depends on both t and y, conceivably. We'd like to approximate the solution phi of t. We've got some starting time a. Usually a is 0. That's why we call them initial value problems, but we can allow for an arbitrary a here. And we have an initial value of y sub 0. We'd like to approximate it over some interval from a to b. Choose the number of steps. This is similar to numerical integration, where you're choosing a number of subintervals. And define the step size, just like with numerical integration, to be the length of the interval divided by the number of pieces. In this case, this is also the number of steps in the method. And define mesh points, just like with integration, to be this: ti equals a plus I times delta t. For I equals 0 through n, there should be a dot, dot, dot here. In other words, draw a little picture here. A is t sub 0. Here's t1, here's t2, etc. This distance here is delta t. This distance is delta t, etc. And the last value of t, tn, is the same as b right there. This is a line, a number line. These are numbers on the number line. These are called mesh points sometimes. Using the initial value, y sub 0, defined by the using the initial value, y sub 0, Euler's method is defined by the following recursive equation. In other words, it's a difference equation, except I'm using a subscript of I instead of n. Y sub I plus 1, the value y at time I plus 1, no, I shouldn't say time, step I plus 1, is the value y at step I plus the change in y at step I. I probably should have had a subscript here as well. And that change in y is approximated by the change in the tangent line. The slope of the tangent line times the change in t. Rate of change times time elapsed. But the slope is determined by the f right-hand side function. That's matching the slope there. Where I goes from 0 to n minus 1, again, there should be a dot, dot, dot there. In general, what happens, this generates n plus 1 data points. Here they are. Once again, we should get a dot, dot, dot. Always forget to check these things on a PC here. And the hope is that y sub I is well or phi of t sub I is well approximated by y sub I. For I goes from 0 through n. Okay? So that's a very brief introduction to Euler's method. I would encourage you to think about what it means, do some reading and that kind of thing. We'll do some examples in lecture 5a. Thanks for watching.